Hello, that is the third lecture from the series Probability Theory for Gamblers. And if you watched our first lecture, we talked about a roulette game. And the conclusion was you cannot win at roulette regularly. The average balance is always in favor of casino. It means that longer you play, more you lose. Now I'm going to state something completely opposite. I think the strategies to win regularly at roulette might exist. If you disagree, please follow my arguments and judge yourself whether I'm right or wrong. I remind you, we try to predict the results of game. For instance, we put every time €1 on the table. We play always single number bet and do it 100 times. Then it is possible to calculate the so-called binomial distribution, rescale it in terms of money, correct for the amount of money spent for 100 rounds, and finally we have the probability distribution of our final results. According to this distribution, you might win €100, most probably, or you might lose up to €100, most probably, but the average balance is always negative. It is minus €2.7. And that is true for any kind of bets. No matter whether you bet on black, red, or you bet on dozens, your probability curve will be always shifted to the negative side, and this shift is always same. It's n amount of money you put in risk times a certain constant, I call it phi. And this constant phi for European roulette is minus 0.027. For American roulette, it's even worse. And this is out of your control. It means that in average, you always lose. What you can control with your gaming strategy is on the chances to deviate from this average. And you can also control your win or loss limits. The reason for your negative average balance is the very existence of number 0 in the roulette wheel. And that is also why casino runs roulette, because they have regular income from that. I think that's all are very logical arguments, and I hope I could convince you in that in the first lecture. The problem is myself, I'm not fully convinced that this picture is valid for all cases. In my childhood, I read a book by Jack London, and this story left certain doubts about the robustness of a roulette game. I remind you, there were two main heroes in this story, Smoke and Shorty. Once they came into a playhouse and watched at roulette players. Smoke, who had a college background, commented, "It's called mathematics that they will lose more than they win tonight." Shorty disagreed. He believed in so-called hunches, periods of time when you continuously win. Smoke remained skeptic. But then he suddenly changed. "Oh, I've got a hunch right now." He smiled, consulted his notebook, and became absorbed in calculation. After a while, he claimed that he discovered a system, and that was the statistical system, nothing to do with hunches. Actually, he simply found that few numbers happen more often than the other ones. And of course, this genial system was working only for the particular roulette table in the particular casino. In this story, it appears that the table stood close to the fireplace, and the roulette wheel was a bit warped. That was the whole secret. This negligible warping can change everything. With an ideal roulette wheel, Smoke is going to lose about 3 cents at each dollar, in average. That is clear from this simple calculation. But Suppose that one particular number is a bit more preferable than the others. Say its chance to happen is increased by small bias. We call this bias alpha. And from this formula, it's easy to see that if alpha is more than 1 over 35, the loss turns to win. 1 over 35, it's about 3% more preferable than the other numbers. It's not much. And if we assume, for instance, that alpha is 10%, then smoke is going to gain in average 7 cents at each dollar. But how to find these preferable numbers and their bias? I think the general idea of the novel is correct. By the way, I believe that's exactly Jack London who is shown at the cover of the book. But with all my respect to him, his text would not help us to find out the preferable numbers. Numerically, this story is not very realistic. The person who can help us is Thomas Byers, an English priest who practiced some mathematics when not so much busy with his service in church. Actually, we know quite little about Reverend Byers. Even this portrait I took from Wikipedia is most probably not real. But what we do know from him is a mathematical work which was published already after his death, and this work influenced enormously the modern science. Especially in 21st century, you can find so-called Bayesian approach everywhere. For instance, consider again the European roulette wheel. There are 37 numbers, and we might assume that the probabilities of numbers to happen are equal. That's logical. The numbers occupy equal segments of the circle, so we don't see any preferences for any number. But Father Byers was a priest, and I think he knew very well that there are many things that sound logical, but appear not true at the end. Yeah, human knowledge is quite limited. This statement is, however, rather trivial and not very valuable. The contribution of Byers was quite different. He posed the following question: can we assign a certain degree of confidence to our belief? Rephrasing that in less theological but more scientific terms, can we calculate the probability that a given hypothesis is true? More specifically, remember in the first lecture we dealt with a game that resulted either in win or in loss, and the probability of win was pi, and probability of loss was 1 minus pi in one round. We knew exactly the pi value. The question was how many successes we can expect from a given number of trials, and the answer was binomial distribution. Now there is a reverse task. Suppose that we know nothing about the pi value. We just experimentally observed n small number of successes from n large number of trials. Can we say something about pi? The answer was delivered by Byers, and this is the following probability distribution. The first impression is that these formulas are quite similar. They are almost identical except of the normalization constant. But the meanings of them are quite different. The first formula is the probability distribution against n small, the number of successes, and the second formula is the probability distribution against the pi value, which is true rate of successes for a given game. So the meanings are quite different. That illustrates well the general wisdom that the probability theory is not about formulas or numbers. It's about understanding of what's going on. I'll try to explain you what is called Bayes' theorem. Explain very roughly without any formulas, just for general understanding. Suppose we performed 1,000 trials of some game and observed 27 successes. Does it mean that the true rate of success for this game is 27 over 1000? Not necessarily. It could be 27, but only with certain probability denoted as a black pillar here. But it's also possible that the true value is, for instance, 31. Let's call it Bayesian hypothesis 31. Let's believe for the moment that hypothesis 31 is true. If it's true, then it should be also some natural variation around 31, some probability distribution, and the part of this distribution might cover the really observable 27 value. Okay, we can calculate that and pick up the probability that the true 31 just eventually showed us 27, this red pillar. And this red pillar we assigned as a degree of belief in Bayesian hypothesis 31. We can repeat this procedure for Bayesian hypothesis 23, 34, or maybe 19, and obtain the corresponding pillars, beliefs in those hypotheses. In this way, we can find the degrees of belief in all possible Bayesian hypotheses, and this is what we are looking for. This is the probability distribution that our true rate of success is this or that. It is centered around 27, by the way. The only thing we should finally do is to renormalize this distribution, such as the sum of these pillars is 1, because it is required for the probability distribution. Congratulations, we learned Bayesian statistics. Remember, in the first lecture, we explored the so-called frequentist approach. In this lecture, we deal with the alternative Bayesian approach. Yes, the modern probability theory involves two competitive approaches, frequentist and Bayesian, and they are not equivalent. In most cases, they lead to the same results, but you should know that there are some cases where frequentist and Bayesian approaches make different predictions. In our case, I think we need Bayesian approach, because we are looking for small unknown deviations from equal probabilities of numbers. What actually can cause such deviations? I guess it could be 1,000 reasons. For instance, environmental influence, like in the story of Smoke and Shorty, or the roulette wheel could be not perfectly balanced, or just a croupier. He drops the roulette ball always the same way, just reflectory. And it is possible that he unintentionally targets some numbers more preferentially than the other ones. Okay, no matter why, we just need to find out a bit more preferential numbers, that's all. And, of course, we should be sure that our finding is not kind of fallacy. Bayesian approach can provide us with a certain degree of confidence. Up to now, we express the uncertainty in some probability distribution. But it might be more convenient to express our random variable as some fixed number, say middle value, plus minus something. There are some useful conventions. They refer to the so-called normal or Gaussian probability distribution, but in principle can be also translated to the most of other distributions. Well, you know, Gaussian is characterized by two values, the middle value and the spread of the data, so-called standard deviation sigma. And we know about Gaussian that the 68% of values are located within middle plus minus sigma. And that's what we call most probably the values are in this range. The next level of confidence is plus minus 2 sigma. Almost certainly, with 95% of probability, the values from this distribution are within this 2 sigma range. And the last level of confidence is plus minus 3 sigma. Almost 100% of values are within this 3 sigma range. With these definitions, let's try to evaluate whether our roulette wheel is perfect or not. Here is a graph of roulette numbers, and the dashed line is how the probabilities should look like if all chances are equal. And we are going to pick up the deviations at least 10% from the middle. You remember, if deviations are less than 3%, it's no use for our game. I performed some simulations, just generated 1,000 times a random roulette number, and plotted the normalized frequency of the number's appearance here. So you might see that the appearance frequency varies noticeably from number to number, although in my model I assume the perfect roulette wheel. And also 1,000 times is rather a lot. I think the roulette wheel is turned about 100 times per hour, so 1,000 trials correspond to 10 hours of running roulette. If we calculate the confidence range, we see that we measure with high uncertainty, plus minus, and that is still 68 confidence range. If we plot 95 confidence, plus minus is even larger. The only way to improve accuracy of the measurements is increasing the number of trials. If we measure that 10,000 times, our 95% confidence range is already quite good. Now let's introduce some inequality. Suppose that the number, for instance 34, is twice more probable than the other numbers. From this simulation you can see that for 10,000 trials we can quite surely detect this deviation with high level of confidence. Stop. Do you think the casino would allow you to do such a long-term statistics? Did you see the caption? The use of electronic equipment like laptops or smartphones is prohibited. They forbid it exactly for the reason I explained to you. They don't want somebody to do statistics at their territory. Also, it is not cheating. It is called advantage play. Nevertheless, you understand, casino wants to make money, not to lose it. Because of that, they forbid electronic calculations in-house. But of course, nobody can forbid you to do some mental calculations in your head. That is possible, but I'm afraid mental calculations for 100 hours with keeping everything in memory is too much. So let's explore the shorter measurements. For instance, watch at the roulette table for 2 hours only. Unfortunately, our simulations show that you cannot measure accurately the probabilities for such a short period of observation. The level of confidence is dramatically bad. But there is light at the end of the tunnel. In our simulations, we actually assume the simplest Bayesian model. We assume that some numbers are positively or negatively shifted independently on their neighbors. And that is probably not very realistic. We can build much more realistic models. Remember, we mentioned several potential reasons for deviations from equal chances in the roulette wheel. And all these reasons very unlikely would affect one particular isolated number. Most probably they would influence a group of neighboring numbers. Well, let's build a so-called two-stage Bayesian model. At the first store, we assume that the shifted numbers are grouped, but we don't know the width of the group. It could be 2, 3 cells or 5 cells, we don't know. There are different Bayesian hypotheses. At the second store, even if we know the width, we don't know around which number the group is centered, whether it's 21 or 36 or whatever. So there are two levels in this model. This model is hierarchical. The beauty of Bayesian mathematics is that you can evaluate the Bayesian hypothesis in both stores simultaneously using the same experimental evidence set. Sounds complicated, but just spend a bit time, elaborate the model, and you will see it is working. Probably even does not require too many trials. In my case, I assume that 5 cells around 34 are twice more probable than the other numbers, and the simulations show that even for 200 rounds we can reliably detect that. Traditionally, I finish the lectures from this series with some detailed business plan of what to do. So, first, find a casino that doesn't care so much about quality of their roulette game. That's maybe not so easy to do because I assume the respectable casinos, they continuously perform their own Bayesian measurements, Bayesian investigations, and they will detect any deviations from equal chances before you could be able to do that. Second, build a realistic Bayesian model for shifted chances in roulette numbers. It must be hierarchical model, not necessarily same as I showed to you, but of the same kind. Third, probably most effort consuming. Train your brains and memory for mental evaluation of Bayesian parameters in minds. That is needed because I'm not going to advise you anything illegal, even confronting with the local casino rules. And last, after some period of evaluation, in case you do detect deviations, bet on the favorite numbers and collect money. Very simple. Simple to say, probably not as simple to perform. But if you will be able to perform all these 4 points, I'm sure you will be winner not only in casino, but in life in general. So, I wish you a good luck.